Long ago, there was a man called Galileo. This lecture's title, by the way, is Newton's Laws. It's not Galileo's, but Galileo lived long ago, and back then, people weren't sure about the nature of forces. And so what people had was this idea of the isolated point. And this is a point in space, it's a vacuum, essentially. They said if there was no Earth, if there was no anything, what would it look like to have a point in space? And they decided that if there's a point in space, it's not moving, because in their opinion, life is what makes things move, and it is the characteristic of life. If something can move, it's alive. But they were wrong. I mean, wind isn't really alive, is it? But that's why they believe, like, the celestial bodies and the heavens, like Mars and stuff. They gave these things, like all of the things they could see in space. They gave them personalities because they believed that they must have some kind of like living essence if they're able to move. Galileo kind of ruined all that because he realized that, okay, well, the argument as it went is you've got a book on a desk, right? And when you push the book with your hand, bear with me because I can't draw hands very well. That wasn't a bad hand. Okay, say you push the book with your hand, then the book moves. In fact, I can do it right. Well, you can't see, but okay. And then when I stop pushing the book stops, right? So they were like, well, stuff moves. It moves because something's moving it. But Galileo realized, well, that's nonsense, because if you have a ball on a table and I push the ball, then the ball just keeps rolling and it eventually stops. And so Galileo realized that there's other forces at work here, like friction. But he also realized that this thing, he was a very clever man, and he realized this thing has a state of inertia, right? And it's carrying itself. It keeps moving. And then many years later, a very clever man called Newton, Isaac Newton, came along and stole his law and called it Newton's first law, which is actually Galileo's law of inertia, and essentially restated it. And it has a very long and ridiculous definition as he wrote it, but I'm going to try and write it more concisely. So it's an object, or all objects even, will stay at rest or maintain their geodesic. It's a good word, that. We'll come back to that in a sec. Unless compelled by a force. Okay? And that's Newton's first law. Newton didn't use these words. Also, it's kind of redundant, Newton's definition, that you say it will stay at rest, because, well, first of all, we'll talk about what a geodesic is. Your geodesic is your velocity, essentially. It's where you're going. It's the straight line you're going in and the magnitude of it. And obviously, space is curved. Well, that's not obvious, but space is curved. But in a non-curved surface, if you move in a straight line, you'll keep moving in a straight line unless a force compels you. And at rest, if your geodesic is 0, then it's 0, It's the same thing. Essentially, you maintain your velocity unless a force compels you. And we can say this is dv, the change in velocity, equals 0 if f equals 0. Okay? And we're even going to define a force in a minute, but essentially, in my opinion, this doesn't even need to be a law because it's part of Newton's second law anyway. And it's also wrong, where, like we'll find out with many of Newton's laws, 3 of them, it's actually wrong. But we'll talk about that in a minute. First of all, we'll just demonstrate it because it's easier to see. And you probably all know this, but it's useful to have this image in your mind. What I've rigged up is this, right? I can zap these. Watch. Z, 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 z. That's me adding a force. Right? And now if you watch this, it's just going to keep moving. And we can wait all day. It's never going to stop moving. Neither is this one. And the reason it's never going to stop moving is if you look here, it's got a mass. But otherwise it's got no drag, no angular drag, no gravity. There's no forces acting on it. The only force that can act on it is me, like this. And I can put something back at rest by just adding another force to the opposite side, you know. We can call this static equilibrium. I'll talk about that at the end if we've got time. So, let's do it again. Right. The interesting thing about this, though, is that, okay, let me as well just quickly be clear. If I put a drag on these things, they will stop accelerating, right? Because that's a... Or not stop accelerating, they're not accelerating, but they'll just stop. So as soon as I add a drag, these things stop. But unless there is a drag or some other force, they're going to go on forever. Okay? Does this make sense? However, oh my god, please go away. Right, this is actually incorrect. This law, and I'll show you why. It's because Newton, if you remember, assumed that the world was absolute and space and time are absolute. And so there's always something to base everything off, right? So in unity, this is true. Everything's based from the origin. But if I am falling, for instance, so I'm undergoing gravity, and I look at another object, if I'm falling, I'll see that object accelerating, you know, because I'm accelerating. So in my frame of reference, in my eyes, if I just have a snapshot of what I'm seeing, this thing is flying up, and it's accelerating up. And we can see that here. If we put the game view on here, and we tell the camera to accelerate, you can't tell whether all the objects are moving or whether the camera's moving. Or I could be accelerating all the objects, or I could be accelerating the camera, and it would look exactly the same, you know, you can't tell the difference. But there's only a force on the camera. If we look here, you can see this camera moving around. Right? This has a force, and that's why it's accelerating. But, so essentially this law is wrong. Because in our universe, everything is relative, or we can't be sure that everything's absolute. So you could add something on the end of this that says, like, compared to a frame at rest. You know, as long as you're not moving, this law holds. Okay? Right, let's move on. So next we're going to talk about mass, because this is really important to Newton's second law. But first, let's define it, right? So the first definition you'll learn as a kid is that mass is volume times density. is how much stuff is in something. And it's really, I don't know why I used to get these the wrong way around, but it's really easy that if you've got, you know, if I've got a square that this big, right, and this is the density, and this is 1 kilogram, then we'll make it double as big, and because it's a cube, you know, when I double this also doubles, and this also doubles. So it multiplied by 8. So you see that this thing, the same density, it's got 8 times the volume, so it's 8 times the mass, so it's 8 kilograms. Whereas if we then look at this, maybe this one's iron and this one's wood or something. This one's less dense. Half as dense, 4 kilograms. Okay? So you can easily take this and say, well, that's the definition of mass. And in Unity, you can actually do this with, in rigid body 2D. Here, there's a thing called simulated. Use automass. And it will try and make, like, you know, it will try and calculate a mass based on how much stuff there is inside the object. Which actually surprises me that you can't change that, because I would have thought that you could change the density of it. But it looks like it doesn't let you do that, which to me is obscene. I can't believe it doesn't let you do that. Maybe it does, but I never use that anyway. I always define my own mass. Okay? But mass, by the way, I hope you guys can see the inspector when I'm pointing at it, or at least it's clear what I'm talking about. Okay, cool. Yeah, because sometimes the resolution, I was worried that the resolution might not be high enough. So yeah, so we never use the magnifier ever again. I told you to tell me that. Right. So we've got mass. Okay, but mass is actually, there are 2 types of mass. There is inertial mass, okay, and there is gravitational mass. And we'll come back to gravitational mass all the time because gravity is a big part of, you know, what we do. But it just so happens that 1 kilogram of inertial mass equals 1 kilogram of gravitational mass. And you might say, Alex, same thing. What are you talking about? Like, why does it matter? Like, this might seem like pedantry, but later on when you get to general relativity, when you talk about what gravity really is, it's bending in space-time, right? And this will go to show that gravitational mass is not actually the same thing as inertial mass. They just have the same value. So what is inertial mass, which is what we actually use? Well, we use both, actually. But what is inertial mass? Well, inertial mass is the ability to resist acceleration. Your mass is how good you are at not moving. That's what it really means. Okay, so if I have a fixed force, you know, we'll just do that. If I have a fixed force and I have a mass of, you know, 10 kilograms, then we've got a force of 1,000 newtons. This force is going to move me it's going to compel me to move at 100 meters a second squared, right? But this force, if my mass is 1,000 kilograms, if I weigh a ton, if I'm very large indeed, then 1,000 newtons is only going to make me move 1 meters per second squared. Okay, I accelerate at this speed. So this mass, and it does matter that, because when you go really fast, when you try to get close to the speed of light, your mass will actually increase because the universe really doesn't want you going faster than the speed of light, and well, it's very difficult to do so. So when you try to go really fast, your mass increases. Your mass gets bigger and bigger. But you'll never see that because you'll never go fast enough for it to matter. Okay? So that brings us on to... So we've defined mass, right? So let's define forces, right? So a force... There are 4 fundamental forces in this universe. There's gravity, which again we'll come back to. There's electromagnetism. There is the weak force. And there's the strong force. These are nuclear, and you're never going to use them. This holds atoms together. So, you know that atoms are loads of protons and neutrons. Well, these protons should shove each other apart, right? Because you know that if you have a magnet and the positive is next to a positive, then they repel. But protons stick together because of strong. And they also, electrons don't get drawn into the middle of the atom because of these forces, right? But they're irrelevant to game development. So we're not going to talk about them. Right, what we're going to talk about is electromagnetism, which is the most important force in your life, probably. Obviously, gravity is pretty important because when I jump up in the air, I like to come back down again. I don't like to drift off into space. But everything else you do is electromagnetism. So that's electromagnetism. All the electrons on the outside of me are pushing against these electrons, and that's why we can't go through each other. There's all these small electrostatic forces. It's German. Deutsch. Okay. So and one demonstration of this is, and also let's keep in mind that gravity is extremely weak. Gravity is a really, really weak force, and I can demonstrate this right now. These are some Dungeons and Dragons tiles I 3D printed, and right, they stick together, right? Because they're magnets. It's neodymium. Now, if I take this, scissors, it's not magnetic. I'm going to put that there. Or maybe that one. And you'll see that it's staying up, right? The entire of Earth, the whole planet, is pulling this down. Earth's 6 million kilograms, 6 billion? I don't even know how many. It's a lot of kilograms. It can't be million. It's going to be like billions or even like... Wait, it's times 10 to the 24. I think it might even be... I don't remember. Isn't it 5 times 10 to the 24? Something like that, kilograms. It's a lot. There's a lot of kilograms in Earth. And every single point in Earth is pulling this down right now. And there's just some teeny tiny little magnet and that's pulling this up. And that's enough, because electromagnetism is so much stronger than gravity. Okay, so this is the main force that we're concerned with almost all the time. But we in Unity just call it add force, typically. Like, all of these little things that are really electromagnetism, we just call it a force. And gravity, we tend to just treat it as an entirely different thing and call that gravity, often. I mean, if you look in Unity, in the inspector, this has gravity built in. So we're just so used to everything just going down. The gravitational acceleration is built in anyway. So, we'll come on to Newton's second law. Let me see how much time we got as well. Okay. So Newton's second law, does anyone know this? Come on. Someone tell me, what's Newton's second law? Go on. Okay. Cool. So, well done. That's wrong, but right, I'll tell you why it's wrong. But it's kind of right. And it's right enough that it will work 99% of the time for almost anything you do. Force is equal to the mass times the acceleration. And we can easily prove this by going into here, and I'll do my little cool tool again. I'll do my force lasers. Now you see the ones that are going really far are the ones with low mass. Right? Oh, I managed to grab it, that was cool. You see this one has a mass of 0.1. Now these ones have a mass of 30. And that's why if I'm hitting with them the same force, they're barely moving, you know? And as soon as... And I'll boing this into... Right, but you see this one, this is not moving, even though this is small. You might have thought, oh, this is small, so therefore it has a low mass as well, like these ones. Because if I bounce this into the ship, you know, it goes flying. But this one's big. It doesn't matter how big the scale is, it matters what the mass is. So let's make the mass small. And now, bing, you know, it goes flying. So I'm applying, well, I'm not applying a constant force. I'm actually, the force I'm applying is proportional to how far away I am. So if I'm right next to something, I give a lot of force. And if I'm far away from something, you know, I give a small force. Okay? So force is mass times acceleration. This is wrong, and the reason it's wrong is that mass changes. Right, so there's a better way of writing it, is what I'm getting at. Right, I suppose you could say this is true, but acceleration, right, is dv by dt. Okay, so this already has a change built in. Okay, whereas mass is just mass. Force, so what we can say is that a change in force is mass times a change in acceleration. But you've got to keep in mind that the mass can change too. Okay, so we'll give an example. In fact, first of all, no. You're okay, you get it. Well, okay, we had that example before where you got an object, you know, the force is 100 newtons and the mass is 10 kilograms. So if I have this in a magnetic field and it's a particle and I'm always pushing it at 100 newtons, then its acceleration, you can say, is F equals ma, divide that by that. Oh wait, no, I'm an idiot. F equals ma, divide that by that, and you've got A is force over mass. So we can say acceleration is force, 100, divided by the mass, 10 is 10. Right, and that's why, you know, a couple slides ago I was using these values, because I was doing F equals ma. Now, what we in the physics community like to say is force equals dp by dt, right? Force is the rate of change of momentum. Now, momentum, you might know as, well, you might not know because I've not taught it here, but you probably do know it at some point. But mass times velocity is your momentum. So momentum is really how much oomph you have. It's like, if you see this thing, and we'll come back to momentum a lot later, but, you know, this thing, it may be moving very fast, but it's not hitting things very much. Whereas this thing, when that hits you, you go flying, you know, that really packs a punch. The small ones are barely even gonna, when the small ones hit the rock doesn't even care. Because even though it's going fast, it doesn't have a lot of momentum. Because it doesn't have a lot of mass. Okay? So momentum is mass times velocity. Now mass can change. So, by the way, this is, okay, there's two reasons why we call it dp by dt. One of them is, light, right? You've got light. This is how we draw light. Light doesn't have any mass. You know, when you get hit by a light, you're not like, I'm being hit by the light, because it doesn't have any mass. But light can actually push things. They're called solar sails, and they can be pushed by light because light has momentum. Because mass times velocity is not actually true. It's gamma mv is momentum, and that's called p. And so before, when I was like, what's position? We'll call it s, displacement. You might have been wondering, why are we calling it s? It's because p is momentum. Why is p momentum? I don't know. It's probably a good reason for it. I don't know why p is momentum, but p is momentum. Well, it can't be m anyway, can it? Because m is mass. So p is momentum. This gamma is relativity, and it's magic and scary, and maybe we'll cover this in a bonus lecture at the end, but you don't need to know that. What you do need to know is that gamma is normally 1, and so mv is mass times velocity. So if you have a rocket, and your rocket has boosters, and your boosters have fuel in them, and it's flying, okay, it's not a very good rocket, I know, but I'm not an artist. But anyway, the fuel's going to go down, right? And once the fuel goes down, the mass goes down. This rocket, most of the mass inside it, well, a big chunk of the mass inside it is this fuel. So when it burns the fuel, right, its mass decreases. So the force makes it travel further. So the more fuel you burn, the less force you need to move it. So I've got an example here of this friend. This is Mr. Meteor. And I'm going to start zapping Mr. Meteor. Right? And you can watch. Right? You see that his mass is decreasing. And he's starting to move more. And we can decrease it even faster. We'll just shrink him. We'll use our shrink ray quicker. Okay, watch this. At this point, you know, he's hard to control because he accelerates quite quickly. So you got to keep in mind that this will rarely come up, but it can come up. And also, again, it's nothing to do with the scale. So this thing is decreasing in mass, right? But it's keeping the same scale. So, you know, I'm zapping it, but you see now it's starting to zap really far, even though it's the same size. I just changed the scale as well to, you know, make it look clearer. Okay, so that's Newton's second law, is that force, any given force, we can define a force as the rate of change of momentum. It's how quickly the momentum changes. But for you, in almost every example you're ever going to use, F equals ma. It's just useful to know this. I don't know if you're going to need this one day, but you might need it for something. You know, something might be losing mass for whatever reason. You might do a simulation where something leaks fluid. Okay. Right. So finally, the meat, the good one, Newton's third law. Okay. Newton's third law, as you all know, for every action, there is an equal and opposite reaction. And you might see this on motivational posters for people being like, oh, if there's negative energy in your life, that means there's going to be positive energy. That's not what that means, right? So if you hear someone who, like, I don't know, if you see this on a picture of a cat, it's probably not accurate, right? But when we're talking about forces, this is absolutely true. So, for instance, this is Earth, and I stand on Earth. I'm not that big, but let's, you know, Anyway, this is Earth, and I jump. When I jump, I push the Earth down, and the Earth pushes me up. We push each other. Now, the Earth has a lot of mass. It's got a huge mass. So when I push it, I exert a force on it, and the Earth's just like, I do not even care. That is a tiny force, and I'm very large. Why do I care about your tiny force, right? But when we have the moon, okay, this is the Earth is pulling the moon in all the time, okay, but there's an equal and opposite force where the moon's pulling the Earth, right? So you know how the moon orbits the Earth, right? Well, the Earth orbits the moon too. It moves in this tiny little loop. Like if we have this point on the Earth, this point will go like this. It would draw a little circle. This one will draw a little circle. This one will do a little circle. Right? And if we look at the sun, which is too big to draw, so I'm just drawing it like that. You can't even fathom how big this sun is. And then here's the Earth. Do you see that? Right? You can't even see the curvature of the sun for how big it is. And we're definitely not far away enough. But the Earth is orbiting the sun, right? And the sun will make some slight deviation because of the Earth, because it's quite massive still. And that's why, the Earth is affected. That's why astrologists love, how Mars has an effect on you, and the spirits. I don't know. They just say some nonsense, right? But this. But you have to respect them. Just don't just because you know that it's not true. Don't start fights with astrologers. It's not worth it, right? But they talk about like, oh, we found a new distant planet. Oh, well, this must affect whether I'm gonna get a job promotion today as well, because this is gonna have a slight gravitational effect on the Earth, and obviously that's gonna change whether my fish dies today, right? So. Right. So that's Newton's third law. And a way we can talk about Newton's third law is with force diagrams. And so you see these a lot. You'll see, you got a mass and it's on here, and there's a force here, and there's this force, and there's this normal reaction force, because this is pushing a force down here, and it's also got a component of force down here. And we'll see these a lot, right? Hopefully you won't actually have to use these too much, but I should teach you this. But luckily we're in a game engine where this is more of a thought experiment than what we actually have to say. We can just see the things for real, so we don't have to rely on paper diagrams. But let's use a paper diagram. Dung, dung, dung. You are an astronaut. And oh no! Your wire broke loose. You were tethered. There's a wire on the station to stop you from drifting out to space. And now the wire's cut. And you have a velocity, oh no, of 0.1 meters a second. Oh god, you're moving. Right? And you're gonna, as we know from Newton's first law, that means that if you're here, you're going to drift out into space. Obviously, there's the Earth, and that's pulling you down, so you'll stay in an orbit. But you're just going to keep going and going and going until, well, you're starved to death, is the main thing that'll happen. Or maybe you'll run out of oxygen. Yeah, that'll happen. You'll run out of oxygen, and you'll die in orbit. So how are you going to get back to the space station? Well, you can throw your shoe. So if you're ever in space, you probably can't throw your shoe, because I'm sure it's attached to the suit and they don't let them take them off, and because it might kill you as you decompress. But let's say that you've got a really tight seal around your leg and you can take your shoe off. You've got 2 shoes on today. You decided before you came out that you have a lucky boot that you strap over your spacesuit. You really like this boot, and you take it off and you throw it. Well, when you throw the boot, and let's say you throw it hard, I don't even know if this is hard, but let's say you throw it at 100 newtons. Okay? Well, that means that you are now going to move this way. Well, you have a force of 100 newtons this way. But the force only lasts for as long as your hand is on the boot, right? So that's at t equals 0. Up until maybe like t is 0.1, you know? After that, your hand's here, and the boot's over here. So there's no more force. In fact, at this point, the gravity of the shoe is actually attracting you, but it's very weak, so you don't have to worry about that. But if you threw it hard enough, you know, this is going to move whatever force you do divided by its mass. It's going to accelerate in that direction. If you manage to, in this short space of time, create a sufficiently high acceleration, then you will fly back to the spaceship, and you will be fine, and you will live. Another example, the absolute classic example, is if we are, oh my god, if we're on an ice rink, okay, and there's person 1, who is an ice skater, and person 2, why is he so annoyed? Right, he's so suspicious. Is this a physics lesson? I didn't sign up for physics, I came here to skate. Okay, so they're both here, and you can look at them like this. And let's say they both have the same mass. They're both 50 kilograms, right? Then this person, they push each other. And this person, they go, ooh! This person applies 100 newtons to this person, and this person applies 100 newtons to this person. So what's going to happen? What happens now? Well, the reason we said an ice rink is because, you know, there's not much friction here, so it's easy for them to push apart. They'll start moving apart, right? So let's look at the forces. There's this force, 100 newtons, and we'll go blue for this one. This force, 100 newtons. So this one received 100 newtons of force, and this one received 100 newtons of force. Right? However, there's also Newton's third law. So this experienced an equal and opposite reaction. So when this received 100, when this thing delivered 100 newtons of force, it also received 100 newtons of force in the opposite direction. And when this force existed, this 100 newtons, there was another one in this direction of 100 newtons. So they don't travel with 100, they move with 200. You know, this is going 200 right, and this is going 200 left. Because not only is the force, you know, there's not only the force that Mr. A is putting onto Mr. B, there's the force that Mr. A is experiencing as a recoil. Now, Unity does not implement Newton's third law. When you hit the ground, when you have gravity, you don't push the floor. The floor doesn't really push you. It kind of does in that you stay still. So that's the one example where it kind of does exist. However, if I have a rocket launcher, right, in a video game, not in real life, and I fire it, and I fire a rocket out, okay, like 100, well, we'll do it as a vector, right, because it's the force is some vector. Right, so we'll say my vector equals 1, 0, 0. I know 1's not very much. Well, we'll say 100. Okay. then in real life, this is the force, right? You then experience my recoil equals minus my vector. So if you want a realistic simulation, then when you fire your rocket, your character, you should do another add force on your character backwards. So you can say, you can say rocket dot add force 100 0 0, or okay, in fact we just do it here. It's easier, right? We can do like vector 3 my force, and then we can say r dot add force. We'll do rigid body 2D some rocket equals find object of type of rigid body 2D as rigid body. Right. Come on, brackets. Okay, right. And then we can say that some rocket dot add force my force. Right? Then, to properly implement Newton's third law, we then say me, as in R is my own rigid body, dot add force, minus my force. And that will give me a recoil. I don't know why it's not. What are you complaining about? Cannot resolve symbol. Have I just misspelled it? Oh my. Yeah, there you go. Right. So there we go. Right. I should have really called it my force, shouldn't I? Right. So now in reality, you care more about game feel than you care about realistic physics. So if you do want to recoil, maybe you do that. But keep in mind as well, your rocket's small, so 100, like, it has a low mass. So 100 newtons of force might actually propel it very far, but 100 newtons to you might not be very much. There's an explosive force. You can also do this. I believe you've got these impulse, and you can do in fact, I'll look what these are because I would never bother using them because I just do it directly. But I'll properly give you a lesson on what's the difference between them next when we talk about force in the future. But yeah, right. So how much time do we have? Not much. Okay. So I'll talk now about what your assignment this week is going to be. Okay. So here we have a ship that is controlled by me. And we're going to talk more in next week next lesson, why this is how it is, right? But you see, I'm moving this and it has quite smooth motion, right? It feels good. If I plug a controller in, which I'm not going to do in case something goes wrong with my drawing tablet, but it's good feeling, right? Then what I can do is I can take this and make it feel awful by flipping a bool. Let me move this up. Okay, we're going to turn off force-based movement. Oh my god, that was crazy. Do you see now? Do you see before it was smooth? My motion was smooth. Like, if I just tap it, it accelerates, it decelerates. It moves in like a smooth line. And now if I get rid of my force-based movement, now too many platformers on the market and other video games do this, especially in indie games. They use this velocity-based movement where you can do this. And when you use force-based movement, everything looks like this. Delicious. And doesn't look ridiculous, right? Whereas in my opinion, this looks ridiculous. Right? It looks like a glitch, no? Like, that motion is... Whereas like this looks smooth and realistic, right? stuff moves like this in real life. Like, it doesn't. You'd be hard pressed to find stuff in real life other than robotic arms that move like this. And even robotic arms move like this, just very, very quickly. In fact, we can probably, if I'm really quick, we can probably imitate this by adding a huge amount of drag and then adding a huge amount of force. There we go. That's like a robotic arm. As long as your drag's high enough that it stops you, and your force is high enough that you're going a long way. And still that looks better than this, right? Let's move it like... Well, I don't know if you can tell it. It's just a little bit smoother, just that slight bit smoother. Maybe it's not as obvious. But this is how, like... So, in my opinion, when possible, you should always move things by forces and not velocities. And what I mean by that is, when you move something by a force... Wait. When you set something's velocity, there's two things I can do, essentially, here, right? Let's grab this script. I can add a force, or I can put the velocity equal to something. Okay? And when I put the velocity equal to, I'm not using forces anymore. But when I'm adding a force, I am. And there's another way you can do it, and we'll talk about that next time, because it seems like we've expired on time right now. I didn't talk about what a great resource hyperphysics is. It's from the University of Georgia State, and it's been around for donkey's years. And you can really get into anything like obviously, I'm not going to teach you the whole of physics on this course, but there may be some reason that you need to know nuclear physics or something. You're probably not going to have to. But you might want to know about sound, you know? So we're doing mechanics, pretty much. So all of these topics are the things we're going to cover. You know, we've covered Newton's laws, if we look mass. It's basically explained what I've explained. Weightlessness. Well, I didn't even explain weight. But we're going to get into that. You know, we can get into orbits. And then, you know, orbits, and then it's its own giant thing with all Kepler's laws and stuff like that. So it's a lot of stuff, but if you were to... I can only teach you what I can teach you within the scope of this course, right? And I'm not going to test you things that I didn't teach you. But for the things that I don't have time to teach you, this site, Hyperphysics, is fantastic, and is free, and physics never gets old, right? Well, I mean, it does at some point, but we're going to do the binary countdown. I bet I can do it. Right, let's go. Oh, no, I can't. Wait, yeah, I can. No, I can't do it. I can't do it. There's too much going on. Right, we'll just do 5, 4, and 3, and 2, and 1. Have a good day. Enjoy the rest of your lectures.